Okay, 5.3. Uh, you can solve problems about bodies resting in equilibrium, so they're perfectly balanced. On this occasion, they are stationary. It means all the forces and actually all the moments are equal to zero. So it doesn't matter where you take the moments along this beam, anywhere you want along this beam, or away from the beam, even in space. So I could take it up here, here, wherever I want to take it. The sum of the moments, even on the beam, whatever, will actually be zero. So when a particle is in equilibrium under the action of a set of forces, the resultant force in any direction is zero. The same is true for a rigid body, i.e. a beam or a plank. In addition, if a rigid body is in equilibrium under the action of a set of forces, then the body will not turn about any point. Okay, when a rigid body is in equilibrium, the resultant force in any direction is zero, and the sum of the moments about any point is zero as well. That's what I've just said. Right, going on to this question. It says the diagram shows a uniform rod. So when it says uniform, it means its weight is evenly distributed throughout the beam. So its weight is acting right at the center. So it's a uniform rod. So that will mean that it has got mass. And you can see it's a 3 meter length and its weight is 20 newtons. So I don't need to put 20 G. It acts right at the center. So it's a 3 meter rod. 1.5 is about there. And it's acting down there at 20 newtons. So it's 20. Resting horizontally, as you can see there, on supports A and C. These are providing upward forces. Let's call that upward force A, and that is an upward force C. And it says A to C is 2 meters. Calculate the magnitude of the reaction of the supports A and C. Now, the beauty about taking moments is you can choose it anywhere you anywhere you want along this beam. You could choose it away from it, but if you choose one of the support points, it gets rid of that force, because that force there, if I choose to take moments about A, that force is acting straight through the fulcrum, the pivot point, and therefore there's no distance, no perpendicular distance, so it's zero. So that goes. Same as if I took moments about there. So if I want to work out the size of the force here, I would say to the examiner, take moments first of all, clockwise is positive, around A. Okay, so what's going on here is the fulcrum I've chose is there, and as I've just said, that force has got no turning effects, it's going right the way through the fulcrum. That one is wanting to rotate this rod around this direction. If this didn't exist, that would want to rotate it around there, so it is clockwise, so it's positive. So I'll start there. The force is 20, and I'm going to multiply it by the perpendicular distance that force is operating at, a distance of 2 meters. This here is wanting to rotate around here, so it is an anti-clockwise, that's a negative anti-clockwise moment, and it is the force C, and it is multiplied by its perpendicular distance is, well, it's going to be 2 meters. Oh, I think I got that wrong there, haven't I? Sorry, that bit there is not 2 meters, it's 1.5. I should really put that as 1.5. Okay, my bad. So that's 1.5. Right, so working this out, I've got 10 times that is 15, 2 times that therefore is going to be 30, and it is take away, and we've got, oh sorry, sum of the moments is equal to 0. Making a right mess of this. Sum of all the moments, because it is in equilibrium, what does it say, rests horizontally, the sum of all the moments will always equal 0 if it's equilibrium. So I know the result of this, which is 2C, is equal to 0. Throw this over, divide by 2, therefore I can see the reaction at C has to be 15 newtons. And you can either take moments at this stage now about this point and it will find this, or you can resolve vertically upwards. Okay, so I want to resolve vertically upwards and say up is positive, and we know we're going to be using net forces, because it's in equilibrium, is equal to 0. So the only positive ones are force A plus force C, which we now know is 15, take away the force 20, and we know the sum of those forces is equal to 0. That gives you -5, throw it over, and therefore A is 5 newtons. And that's the answer for the first one. Okay, there's nothing underneath. Right, over the page. Second question. Again, a uniform beam AB of mass 40 kilograms. So we're going to need 40 G. So it's acting right at the center. It's uniform. And it is 40 G. And length 5 meters. So I know this section in the middle here has got to be 3 because one either end. It says, in fact, yeah, so that's 3, so that's 1.5 before I forget, from there to there, and 1.5 from here to here. And it says a man of 80 kilograms stands on the beam at E with magnitude of the reaction D is to what, right? So I don't know, we're going to put him 80 kilograms, so it's going to be 80 G. 80 G. And we don't know where he's standing. It just tells us by modeling the beam as a rod and the man as a particle, find the distance A to E. Okay, so I want to know what distance this is, so I want that answer. If that's the answer I want, I'm going to set that to be X. Now you're also told here that the reaction at D is twice that of the reaction at C. So now I can say that I've got a force here and a force here. So the reaction at D is twice that at C. So if I call this force here R at C, then D is twice that. So that's going to be 2R. Okay. So straight off, I'm actually going to find out what R is by just resolving, because it's an equilibrium. So resolving, up is positive. Okay, and then using net forces is equal to 0. What you've got going on there, the only positive ones is R plus 2R minus, we've got the 40G minus your 80G, and we know the sum of those forces equal to 0. So I've basically got 3R is equal to 120G and R is equal to 40G. Okay, so we've got that. I'm not going to go any further with that. The next thing is I've got to find X. So I'm going to take moments. You can either take moments about here, we could take it here, 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 or here. It's sensible, or here. And if I take it here, I'm going to have to use this, 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 and this. It doesn't matter. But if I take it from here, then it negates this one here. If I take it there, it negates that one there. So it doesn't really matter. You know what? I'm going to take it about A. Okay, so I'm going to say positive is clockwise, and I'm taking it about A. So the first clockwise one I come to is these, the weight and the man's weight. Okay, they're wanting to spin it around point A in a clockwise manner. So in brackets, the first one is 40G, its force, times by its perpendicular distance is 1.5, plus the 1 is going to be 2.5. Then plus, and we've got the man's weight is 80G, and this time it is times by its distance, which is X. And then the others, this is a negative because it's anti-clockwise, it's wanting to spin it around this way. So it is the force R, which we know is 40G, and it is times by its perpendicular distance, which is 1. And then minus this one here, which is 2 times that, is 80G, and that is times by its perpendicular distance. Well, if this is 5 meters, then this must be 4 meters. Okay, so let me just check that again. Everything's all right there, and we know the sum of those forces is equal to 0. Okay, in fact I might be able to squeeze that on down there to make it a meter. 0. So working this out, 2 times that is 80, half times that is 20, so that's 100g. I've got plus 80xg. I've got minus 40g. I've got minus 320g is equal to 0. So you can see I can get rid of all these g's, they're all gone, and I end up with basically 80x is equal to, and I end up with 40 combined with that is minus 360 plus 100 gives you minus 260. Throw it out, it becomes a positive 260. So all I've got to do is divide through by 80, sorry, and I end up with 26 over 8, which is equal to, divided by 2 again gives you 13 over 4, which is equal to, I could work that in my head, what's that going to be? That's going to be 3.25 meters. So I've got the distance that must be, the man must stand there, so that the reaction I've got here is twice the reaction I've got here. Okay, I hope that process makes sense. Again, the setting out is very important. Okay, underneath, no questions. Next example, right, example 9. A uniform rod AB of length 4 meters as a mass of that. So first of all, uniform rod 4 meters, and it's uniform. The rod is uniform, so it means its mass is right at the center. It's 12 kilograms, so I have to put 12g. Resting in horizontal position on supports C and D, AC equals DB, right? Which is that? So it's C and D. So I've got A to B is 4 meters. Its supports are there, which is 0.5, and that is C, and DB is also that. So I've got same thing down there. That is D. That I'll put on top. That's 0.5. When a particle of mass m kilograms is attached on a rod at point B, the rod is on the moment about right. It's on the point of turning. This is called limiting equilibrium about D. So for that to happen, it's got the mass is put on point B. It is here. So I know the mass is m, and therefore its weight is little mg. Now, the really important thing here, this is called limiting equilibrium. Oh, let's just change that colour, sorry. It's really important to note that there is telling you you are in limiting equilibrium. Limiting equilibrium. Okay, now if that's happening and you're saying it's on the point of turning here, so that's where you're about to pivot around, it means that there is no more support offered by the other support, so that now can be negated. It has no effect. That in essence is exactly what you've got going on. Okay, so that only applies when you're on the verge of pivoting about D. If you're about pivoting about D, this is offering no support. So when this type of situation occurs, we've got to find the value of m. So I'm just going to take moments. So take moments, and obviously the sensible point will be to take moments about D. You don't have to though. Okay, if I take about D, the force going upwards, the force D is negated. Okay, the force D is negated. It's got no, it's going right through the fulcrum. So what I've got here is the positive one, is the weight, the mass being added. So that is the weight, which is mg, multiplied by its perpendicular distance is 0.5. And the other one is an anti-clockwise turn, so it's negative the force, which is 12g, multiplied by its distance. Now this is a 4 meter length, this is 2 meters here and 2 meters here. Okay, so if this is 0.5, it means that is 1.5. And we know it's in equilibrium. Even though it's in limiting equilibrium, it is still equilibrium, so we know it's not turning, so it is still 0. So working this out, I end up with 0.5 mg minus 1 times that is 12, half that is 6, so it is 18 g is equal to 0. Get rid of the g's and we'll replace that with a half, and you can see that I end up with 2 times that gives you, therefore the mass must equal 36, and mass is measured in kilograms, so 36 kilograms if you rearrange that equation, and that's what we get for that. That mass has to be 36 kilograms to make it so it is just on the verge of tipping. If that grows any bigger, and you are going, this whole beam is going to rotate around and spin round. Okay, any less than that, and this force is going to start. What the resting support here is going to start taking some force, have to provide some force there. But perfectly at that stage there, then that is not needed. Okay, that's what limiting equilibrium means. Right, over the page, next question. Right, again, you've got a set number of questions here. You must set them out in the same way I'm doing, so uniform way, be aware about it. You know, how I've set it out. Be careful, structure your answers correctly, and any problems, email me or message me via Google Classrooms, but give it a go. Okay,